Every second of every day, a roaring ball of nuclear fire showers our planet in heat and light. But the math behind that light reveals a problem. If we calculate the energy using the standard laws of motion, the sun is entirely too cold to shine. Inside a star, the engine runs on collision. Hydrogen protons must move fast enough to crash into one another and fuse, creating the heavier elements and energy that we see as sunlight. Protons carry a positive electrical charge, and like the matching poles of two magnets, they repel each other with incredible force before they can ever make physical contact. This diagram illustrates the problem. The spheres represent protons, facing the steep Coulomb barrier. Even at 15 million degrees Celsius, the sun's core is too cold to give them the momentum to cross that peak. They roll partway up and are repelled back down. Under these classical rules, protons would bounce away from each other forever. The universe would remain dark, and the conditions for life would never exist. Solving the solar paradox requires us to leave the world of large, solid objects and shrink down into the subatomic void. At this scale, the rules change. We encounter wave-particle duality, where protons stop acting like solid billiard balls and instead behave like vibrating clouds of probability. This behavior was first captured by Werner Heisenberg, who demonstrated that at the quantum level, a particle's exact position can never be perfectly defined. Erwin Schrödinger later provided the mathematical framework for these probability clouds, defining them as wave functions. A proton's location is never absolute. It exists as a spread of chances across space, a quirk of nature that opens a loophole in what was previously considered an impenetrable boundary. When we revisit the Coulomb barrier through a quantum lens, we see a probability wave approaching the obstacle rather than a solid object. The wave doesn't just bounce, it enters the barrier, its vertical amplitude shrinking rapidly as it moves through the resistance. Physicists call this process exponential decay. If the barrier is thin enough, that decay doesn't reach zero. A tiny tail of the wave emerges on the other side. Since the wave represents probability, that emerging tail means there is a real, measurable chance for the proton to spontaneously materialize on the far side of the wall. The particle doesn't need the energy to climb the hill. It simply bypasses the repulsion field and appears on the other side. This is quantum tunneling. It is the specific mechanism that allows protons to touch, igniting the nuclear fusion that creates a star's light. This creates a scale paradox. For any single pair of protons, tunneling is an astronomically rare event. So how does the sun produce enough energy to power a solar system? The answer lies in the sun's unfathomable scale. Its core contains roughly 10 to the 56th power hydrogen atoms, all constantly colliding. Multiplying an infinitesimal tunneling probability by that many protons guarantees a steady, massive rate of fusion. This extreme rarity actually keeps us alive. It creates a bottleneck that forces the sun to burn its fuels slowly and reliably over billions of years, rather than consuming itself in a single, instantaneous flash. Modern electronics now use this same quantum loophole to move information. Your USB flash drive relies on quantum tunneling to push electrons through solid insulators, trapping them to store your data even when the power is off. Scientists also use this tunneling current in specialized microscopes to sense individual atoms, mapping the surfaces of materials with atomic precision. The next time you step outside, remember that the warmth of the sunlight on your skin is the physical result of quantum mechanics in action.